Physicists are closing in on discoveries of a lifetime, from the mystery of dark energy to the search for dark matter.
It is a crucial picture in our understanding of how the universe works.
And as Forbes places the University of Florida in the new Ivy League, UF professors and students are on the leading edge of something that can rock our world. They're changing matter with freezers and magnets, and tracking ripples in space and time.
It's a very hot place to be in general relativity.
We'll start with a giant space antenna that could help explain everything in this edition of Breakthroughs in Science. Well, the University of Florida is on the leading edge of something that could blow your mind, especially when we introduce you to Lisa. But we need to set the stage with a quick point on gravity. See, Einstein proved that space and time warp around matter, and that curvature of space gets more intense the heavier something is, like the Earth beneath our feet. And that's what we feel and see with the pull of gravity. And Einstein said that big objects also will produce ripples in space and time called gravitational waves.
It is a stretching and squeezing of space-time, the fabric of the universe.
So more than 30 years ago, the University of Florida partnered with Caltech and MIT to build a gravitational wave detector to prove that Einstein was right.
Yeah, UF's played a really, really large role right from the beginning. UF provided a significant amount of the optics and the optical design of the interferometer.
Well, an interferometer is a device that fires and splits lasers in different directions, making it an incredibly precise ruler. So when a gravitational wave rolls through, the arms of the device, the laser ruler, detect the stretching of space. And so they built what's called LIGO, one very long interferometer in Hanford, Washington, and another in Livingston, Louisiana. And in 2015, LIGO detected its first gravitational wave. Here's the chirp from Washington, and here's the chirp from Louisiana. And it carried enough information to reveal that that wave came from two black holes crashing together 1.3 billion years ago, because it took that long for the wave of the collision to reach Earth back in 2015. Now, this is an exaggerated animation to illustrate the effect of a gravitational wave. The actual stretching of space-time was within a thousandth of the length of an atomic proton. And LIGO still detected and measured it with an algorithm developed by UF professor Sergei Klemenko.
It's very rewarding. And I think that this is the most exciting part, to see something new.
And after a Nobel Prize and more gravitational waves rolled in, it drove this plan to build a much larger detector to reveal so much more.
And get the clearest picture yet of how the universe came to be the way it is.
And that brings us back to the University of Florida's labs. It's time now to meet Lisa. It stands for the Laser Interferometer Space Antenna. And this one will reach millions of miles through space. UF, NASA, and the European Space Agency and others are making this as we speak.
So what we're seeing right now, so as Alex was just saying, we have pendulums and spring systems that are suspending everything inside of the tank. And all of those things have their own sort of resonance.
On one side of UF's Lisa lab, they fire green lasers into iodine to make precise measurements of jiggling molecules. And on the other side, you'll find optical benches with lenses and mirrors and all kinds of electronics. They fire and bounce lasers we can't actually see until they reveal them with a special paper, because they're near infrared.
And so he blocked the beam. We no longer have a transmission beam that we can look at.
And as you'd expect, their sensors are incredibly sensitive to any vibrations.
You can see directly the effect of the foot traffic.
It even picks up foot traffic as classes change all across campus. And right now, they're improving the sensitivity of the detectors and testing Lisa's components.
Our biggest project is testing the dimensional stability of the telescope.
Well, the telescope is buried in thermal shielding to replicate a space environment as they test how well lasers will pass through it.
All those things down there, those are pumps pulling out air of the vacuum chamber. We have blankets for thermal insulation.
And this is how it'll all look when they're finished. Spacecraft, millions of miles apart, will form a gigantic triangle in space, and they'll bounce lasers as LIGO does here on Earth, but Lisa will detect waves with much longer frequencies. That means it should detect supermassive black holes crashing together, and who knows what else.
We know surprisingly little about the universe, and it's very hard to probe the very, very early times and how everything began.
Yeah, Lisa will detect waves formed near the beginning of time and help us figure out how that all went down. And that's especially important now that the James Webb Space Telescope is revealing galaxies that appear to have formed earlier than we thought they could, challenging our concept of their creation.
Now we can see the beginning of the universe, and not everything agrees.
And neither do our basic laws of science. Right now, laws that govern the small world of particles clash with the laws that govern heavy objects here in the scale of everyday life. So there appears to be a missing link that could unify those laws, and physicists are trying to find it.
The key question is whether we can have something that's actually observable or measurable.
And that's where observing and measuring waves from supermassive black holes can do the trick, because think about it, that's where the worlds of the very heavy and the very small combine. And that's where Lisa could revolutionize our understanding of nature.
And one of the key discoveries we could make is to find something that is different from the fundamental laws of physics as we currently understand them.
But we're getting way ahead of ourselves there. They have to finish Lisa first, and they plan to complete and launch Lisa in the mid-2030s. Coming up, spinning galaxies reveal a problem in physics that UF researchers could solve by detecting dark matter. We have some big problems in physics that scientists need to clean up. For example, we can determine the mass of distant galaxies and precisely calculate their spin. But then look at this. We can also see those same galaxies spinning much faster than the laws of physics say they should.
They are not behaving anywhere like we expect they should. They should obey Newton's laws. Newton's laws have held up so well, up to small corrections that Einstein showed us. And the fact that they're not obeying those laws suggests to us that there's something out there we're just not seeing.
And it's also bending and warping light from distant galaxies, which tells us there must be these huge clumps of matter along the way that we just can't perceive. And since we're in the darkest of what it might be, we call this dark matter. And here's another problem that needs to be cleaned up. See, we know the universe, of course, is expanding, but instead of gravity slowing down the expansion because gravity attracts things back toward one another, well, in 1998, we discovered the expansion is inexplicably speeding up.
Accelerating, and that's the dark energy content.
University of Florida professor Dr. David Tanner is one of the world's top experts in the search for dark matter, globally recognized for his work on this. He's co-founded UF's Dark Matter Initiative. He did that more than 40 years ago, and he helped design these devices that are looking for dark matter here today.
It's never been detected, but the theoretical aspects of it are pretty well worked out.
Well, mathematically, most of the universe is made up of a lot of stuff we cannot perceive, but it's got to be there and must have been around since the beginning of time. In fact, cosmologists say that dark matter helped pull visible matter together, kind of like invisible fingers of a sculptor that shaped it into dwarf galaxies, which then collided to form larger galaxies like our own in what's really just a fraction of existence as we know it. Here's the jaw-dropping pie chart. Gravity and math reveal the observable universe is mostly comprised of dark energy, 68%. Dark matter makes up 27%, and visible matter, what we can see, a mere 5%. We're 95% of the dark here, which leads to all kinds of mind-blowing theories.
There's a possibility that the whole universe is one giant black hole and we're in it.
Well, Dr. Tanner leaves those kind of possibilities to the theorists, while he and these UF students focus on detecting dark matter on Earth. Graduate student David Sadek is looking for one type called WIMPs. In theory, these release gamma rays when they collide and annihilate.
This experiment is very sensitive, so it's currently located underground in a snow lab in Sudbury, Ontario, Canada.
Meanwhile, Dr. Tanner helped develop axion detectors. Axions are a different type of dark matter that's showing particular promise in finally being confirmed and revealed. And University of Florida launched the experiment called ADMX, which stands for Axion Dark Matter Experiment. and it's grown into an international partnership with the hub now based at the University of Washington.
An axion is a particle which is a candidate for dark energy. It's also a candidate for dark matter, and that's what drives a lot of the experimental work here in the ADMX collaboration.
Here's the whole idea. If axions do exist, as equations suggest and scientists suspect, well, then they would release photons when they decay, and a strong magnetic field would stimulate their decay. So, ADMX uses powerful magnets to stimulate an axion's decay and then use microwave cavities with superconducting amplifiers to catch the photon release. But to detect that little extra power coming out of the cylinder or the cavity, you have to tune it to the right frequency for axions. And see, that's the real trick, because we don't know yet what an axion-specific frequency would be.
Exactly. Yeah, it's like driving through the desert in the middle of the night and you're trying to find an AM radio station so you can stay awake, and you tune, you hear nothing but static, you tune, you hear nothing but static, you tune, you hear this very weak voice, but you found a radio station.
And by that analogy, when you find the station, you hit the jackpot and finally clean up the problem in physics.
There's only one frequency that works. It's not more than one station. And the possibilities are many, and we've been slowly tuning along.
At what point do you know, okay, I've cranked through the entire range and it's not there, so this must not be, or, by gosh, we finally found it? How long is that going to take?
Well, it could take another 10 years. I mean, as I say, the experiment...
That's not that long, really.
Not that
so
long.
You think we could nail it down in 10 years?
Yeah, I think so.
Because of how much they've already moved along the dial, and because they're significantly expanding the detector system. UF graduate student Alex Hipp is working on the model of what they'll build on a much larger scale at the Department of Energy's Fermilab.
It would be the high point of my life, probably. One of the biggest discoveries in physics, probably for the coming century.
For example, detecting a lot of axions could provide observable experiments to help nail down string theory, which holds there are actually 10 or 11 dimensions of existence, though we can only perceive length and width and height and the passage of time.
If indeed we start finding many of these axions in our experiments, the only explanation I could think of is, in fact, it's a consequence of string theory.
The detection of axions could help us pinpoint a theory of everything, while the technology used in these devices could also help launch the age of ultra-fast quantum computers. And just imagine what engineers could do with the receivers they've already built.
We have a receiver which is sensitive to yoctowatts. And if it was in the front end of your cell phone, and you took your cell phone to Mars and turned it on, you have 4 bars from a station on Earth. That's how sensitive it is.
All in the search for axions, which brings us to why they call them axions.
It's named after a brand of dish soap.
That's right, particles named after a brand of soap to clean up the problem in physics. Coming up, UF and FSU joined forces with the Department of Energy to run the largest and highest powered magnet lab in the world. We'll show you how their experiments can transform our lives in ways you may not believe.
Good morning from a frigid Sioux Falls, South Dakota, where it's 24 degrees below zero this morning.
That's cold enough to change a cup of hot water to frozen dust. Now, we can see how water turns from a liquid, of course, to a solid when it drops below freezing. But if you keep going, you're getting colder and colder and colder, materials will continue to change. And that's what University of Florida researchers are studying with powerful refrigerators and magnets to transform our world.
The physics starts to change. Things get a little different and strange.
And scientists observe the strange things that happen in extreme conditions so engineers can figure out how to make the next great technological leaps in normal conditions.
Well, first of all, it's going to make much more computing power available and smaller for everyone.
These walls lined with tubes and vacuums and buttons are part of the National Mag Lab. It's a partnership between Florida State University, the University of Florida, and Los Alamos National Laboratory. MIT and others wanted it, but Florida beat them out, giving FSU and UF something really special.
We are absolutely unique in North America to start, and then also we have unique capabilities that extend worldwide.
In concept, it's actually pretty simple. Think of a household freezer, but much larger and stronger.
If it's a refrigerator like at home, we have a large number of mechanical pumps that provide the vacuums that we need.
And unlike household refrigerators, their dilution refrigerators use much more potent coolants.
We use a mixture of helium-3, helium-4 gas, those special isotopes blended to get this refrigerator to run.
They also add baths of super cold liquid helium.
It looks like your thermos bottle for your coffee, same principle, but the first layer inside is 4 Kelvin, it's liquid helium temperatures.
And they put samples of material inside the freeze chamber and then zap it with intense electromagnets which further cool and slow the electrons within. And that part's also pretty simple in concept. To make an electromagnet, you could just run a copper wire from one side of a household battery to another. Electrons take off spinning through the wire, creating electrical current, and you can feel the outer force of those spinning electrons as they stream through the wire in the form of a magnetic field. And the more current you pump through the wire, and the more you coil the wire in loops, the more you line up the spins, and the stronger the magnetic force becomes. Well, that's the same concept the MagLab uses.
So now with Bay 3, you can actually see the insides.
But instead of loop wires, they use stacks of superconducting copper and silver disk to line up and intensify the electron spins, and they use far more electricity to jack it up.
This is doing the same type of measurements, and you can see here, this one's actually running an experiment right now.
From here, they freeze and magnetize a sample of something like graphene, because they can peel that off in thin layers around 1 atom thick, and that makes it sort of two-dimensional and easier to see. And the super cold temps and intense magnetic forces slow down the speeding electrons inside the graphene, and that removes the blur of movements that otherwise conceal how they kind of wiggle around. Scientists compare it to burning off a heavy fog to reveal the details of a hidden city within. Or Dr. Meisel likens it to weeding a garden as you get about as close to absolute zero as you can possibly get.
So every time we lower the temperature by a factor of 10, we weed our garden 1,000-fold.
And that exposes the inner secrets of matter, which gives us knowledge to alter and optimize and control matter to enhance our lives. In general, that's what we call condensed matter physics, which has already helped us develop lasers and MRI machines and LCDs and other innovations we now often take for granted. And the work they're currently doing could lead to much, much more, like levitating trains that could travel as fast as jets.
Those high-speed trains, you're reducing the friction that it has with the ground.
And studying the superconducting material that forms in extreme cold could also lead to producing superconductors at room temperature that reduce electrical resistance and make our energy systems far more efficient. And it could also lead us into the age of quantum computers that harness subatomic particles called qubits.
There's a large variety and different ways to make a qubit.
And those qubits compute exponentially faster than the most powerful systems we use today. And we know this because of condensed matter physics that has already helped develop the early prototypes.
So those particular quantum computers that are operating that you mentioned now are normally operating at or near about 10 millikelvin.
Developed in ultra-cold environments like this, and now being studied and re-engineered for future widespread use at room temperature as we speak.
It's kind of fascinating.
And for all the innovations we expect this work to ignite, it also carries the promise of new and unexpected discoveries that could also blow our minds.
And we need to explore our frontiers all the time, because history has told us when that stops happening, those civilizations collapse upon themselves.
The National Mag Lab is funded in partnership with the National Science Foundation in the state of Florida. And the facilities at FSU and UF host experiments from scientists all around the world, and they offer some public events and tours throughout the year in both Tallahassee and in Gainesville. And you'll find the details at nationalmaglab.org. Coming up, we'll sit down with UF Distinguished Professor Dr. Cliff Will, one of the world's leading experts on gravity. Dr. Cliff Will won the Albert Einstein Medal for his contributions to general relativity, and he's part of the UF team that's made some striking discoveries in the world of gravity.
University of Florida, the physics department has a very long history of work in my field, general relativity, and in recent years has been involved in the detection of gravitational waves.
Just by sensing the wave of gravity, how can one tell where the wave came from?
You can by having multiple detectors around the world. because if a wave comes from some direction, it will arrive at one detector before it arrives at the other, depending on how they're oriented relative to the direction. And so with 3 of them, and there are 2 in the US, 1 in Europe, you can then triangulate and figure out where the source was.
The universe is expanding. We found out as of the late 90s that not only is it expanding, it's accelerating. How can that be if gravity attracts?
So, well, there are 2 possible answers. One is what people label dark energy, a hypothetical substance that has this repulsive behavior. So it makes the universe expand faster and faster and faster because it's constantly, in some sense, pushing out and pushing things to go faster.
Something we don't know is working against gravity.
It's working against gravity. The other possibility is that Einstein's theory, as successful as it has been in many, many experiments, needs to be modified on these largest scales of the universe as a whole.
We'll have more with Dr. Will and the other UF professors' work on Fox 13 News. And if you've missed any of our 30-minute science shows, catch up by streaming them on the Fox local app. And thank you for watching this edition of Breakthroughs in Science.